Okay, good morning everyone. Great attendance for 9 a.m. on a winter Friday morning. Well done, good. Right, so today we're going to go over the last of the three new functions which are introduced in this course, which is the curl. In a similar way to the way that the gradient and the divergence, there's a hint to what they are in their name. There's also a hint to what the curl is in its name. And the curl gives you a measure of the microscopic rotation of a vector field. And the word microscopic is important here, as we'll see during the course of the lecture, because it's not always the case. This is a bit analogous to what we were talking about yesterday with the divergence in the electric field. It's not always the case that you can visualize your vector field and go, yes, that vector field is rotating, therefore the curl must have some positive or negative value. Of course, the curl has a handedness because it's a rotation. It is in fact the case that sometimes you will have a vector field where there is a large scale rotation. However, the curl of that vector field is zero. So always bear in mind that although the curl, you're correct in thinking that the curl measures the rotation of your vector field, it's measuring the microscopic rotation of the vector field. It's measuring the rotation at an infinitesimally small point. Okay. Now, when we talked about the divergence yesterday, I went through the derivation of the divergence as the limit of the surface integral of the vector field around some point in the field where I shrunk that volume infinitesimally small. The curl, in some sense, is the limit when you take line integrals around three axes around a point and shrink those lengths infinitesimally small. I'm not going to go through that derivation today, but that derivation will, in some sense, be in the final lecture on Stokes' theorem, which will be this time next week. Okay, so to remind you once again, then we use our old friend Nabla. To calculate the curl, and the curl of some vector field can be written curl F. It's also written as the cross product of Nabla with that vector field. Okay. So the three operations, the gradient is the operation of Nabla on a scalar field. The divergence is the dot product of Nabla with of the vector operator Nabla on a vector field, and the curl is the cross product of Nabla with your vector field. So if again your vector field is defined as if it's defined like this, then curl of that vector field is the determinant of this matrix. And you can see that it is, in a very real sense, just the cross product of this vector operator with the components of your vector field, in the same way that the divergence really is the dot product of the Nabla operator with your vector field. So really, sometimes people have trouble remembering the definitions of grad, div, and curl. But all you really need to do is remember the form of that vector operator, and remember that, you know, one is just a simple operation on a scalar, one is the dot product, and one is the cross product. Okay. So as I say, the curl is measuring the microscopic rotation of your vector field around a given point. So if we look at the individual components then of the curl, then we see that the I component is d of fz by dy minus d of fy by dz minus j times d by fz of dx minus d by fx of dz plus k d of fy by dx minus d of fx by dy. So your curl returns a vector. Your vector, in this case of Cartesian components, has three components, has a component in each of the I, j, and k directions, as you'd expect for this coordinate system. Now, if you look at what those individual components mean, we see that the component pointing in the I direction, in the plus x direction, tells you about the rotation of the vector field in the plane which is perpendicular to that. So the component in the I direction is telling you about how much your vector field is rotating in the in the YZ plane. Okay? And similarly, your J component is telling you about how much your vector field is rotating in the XZ plane, and your K component is telling you about how much your vector field is rotating in the YX plane. Okay? So what this operation does is it takes your 3D vector field, which has vectors pointing in all different directions as a function of position in this vector field, and it breaks it down into the rotation, the values of the rotation in each of your three orthogonal planes, okay? And then those represent the values of the curl in each of your three directions. Later on in the lecture, I'll show how the quantitative value, the magnitude of the curl, actually also does represent something in terms of the rotation of a solid body. Okay, so it's a good thing to know what the sense is of these operations. It's also a good thing to have some idea about what the quantitative values mean. Okay, so this is the curl. That's hopefully what I just wrote on the board. And the key point then of the three operations which we consider in this course is that the curl is the one that takes a vector field and returns another vector field. Okay, so let's have a go at some simple conceptual ideas about what the curl might be. So here's a representation or a sketch of a vector field. We're just considering a two-dimensional vector field here. So this could be the x and y axes, in which case our component of curl, the only component of curl, would be in the k direction, because you'd be measuring the rotation in that plane. So if this is a vector field in the xy plane, then you can imagine that at any point in that vector field, you would put in a tiny little paddle wheel, and you would see what direction it was rotating, and you would see at what rate it was rotating, and that would be telling you about the curl in that direction. So it could only be rotating in one of two directions, which we call the handedness of the curl. So there would be a positive curl upwards or a negative curl downwards, and the magnitude of it tells you about the rate at which it's rotating. And as I said, later on in the lecture, I'll explain how you can understand that more quantitatively. And again, just to emphasize the point, it is the microscopic rotation. It's not necessarily the large-scale circulation of the field. So let me just show you some examples then. So here's a simple two-dimensional vector field. F equals yi minus xj. So the basic characteristic of a rotating vector field is that you have the I term, that is the component in the x direction, has a y in front of it, and the component in the j direction has an x in front of it, and then one of them will have the opposite side to the other. Okay? That's the basic property of a rotating field. So if I take this two-dimensional vector field, F equals yi minus xj, then I see that the field has a large-scale rotation like this. Now this is one of the nice examples where the large-scale rotation and the microscopic rotation of the vector field are in the same sense. So if you take the curl of this vector field, it's a very simple two-dimensional determinant, you find that it's 2k. And again, if you're taking the curl of a vector field in some plane, your curl is going to be perpendicular to that plane because your axis that you're rotating around is always going to be perpendicular to the plane. That's what you're measuring. The curl of this field then I've represented by arrows in this graphic here, and you can see that the curl of this field is uniform across the field and has a certain sense, which means that the field is always rotating like this. So although you see a large-scale circulation in this field, every paddle wheel, that paddle wheel would be rotating in the same direction and at the same rate throughout this field. Here's another example then of a field. So I have a field where I have f is minus x squared j. So this is not a field with an obvious large-scale rotation. And in this field you see that the vector field, if you plotted it out, it has vectors which are growing downwards as you go to large x, but also growing downwards as you go to negative x because you have the x squared term. The curve in this case has a different sign depending on which side of x equals 0 you plot it. Okay? So on this side, it's just like the previous plot. Particles would be rotating like that at any given point. But the field is growing, so the rate at which they would be rotating would be growing the further you move away from the x-axis. On the other side, however, and you can get a sense of this from looking at the field, the rotation would be in the opposite direction. So here the particles would be rotating like this, and on this side they would be rotating like this. They grow, the magnitude grows in the same way as it does on the positive x side, but the sense of the rotation would be the other way around. So again, another way to visualize this, which is similar to the paddle wheel case, is that if you're thinking of a 3D vector field, and again I use the analogy that it's actually a fluid flow, although very rarely do you actually come across fluid flows in the examples that you do during your degree. Normally it's fields, but imagine it's a fluid flow. If you placed a very small light ball, spherical ball in that flow that had some kind of pitted or matted surface, so the flow as it went past it caused the ball to rotate, then the curl represents the vector which you get, which is the curl. It represents the axis along which the ball is rotating, and the magnitude of the curl tells you how much that ball is rotating. Okay? So assuming that your ball wasn't moving with the large-scale motion in the flow, the curl tells you how much that ball would be rotating and around what axis. Okay. Right. So if you want to know what is the curl in some arbitrary direction, then you take the dot product of the curl with that direction. So if I consider, in this case, I consider some vector u, then the rotation of my vector field f along the axis given by u is simply the curl dotted with that direction. So again, this is another way to visualize this then, is imagine we have our microscopic ball sitting in our flow, and it's rotating in a sense and with a magnitude that tell you about the total rotation of the field in all three dimensions at that point. If I then were to spear this by putting, let's say, a rod right through it, so it could only rotate around that axis. So now this axis here, this blue line, is pointing in the direction of our vector u. It can only rotate around that axis. The amount of rotation that you would get around that axis is the dot product of the curl with that vector. So this is in some sense a little bit analogous to the directional derivatives which we did when we were considering the gradient. Where CF means compared to, so the gradient of some scalar field, the amount by which it changes in a particular direction is the dot product of the gradient with that direction. You'll recall that we did that earlier on. Okay, so let's actually calculate some curls in order to get some better feel for what's going on. So we'll do an example then. We'll say A is equal to x squared, y squared, z squared I. plus y squared zj plus x squared z squared k. And we want to work out then what is the curl of A. So the curl of A is the determinant of the matrix I, J, K. By dx, d by dy, d by dz of our three components here, which are x squared, y squared, z squared, y squared z, and x squared, z squared. So then we get that our curl, so you should just get used to writing that the curl of the field is the cross product of nabla with the field. For some reason, this looks simple, and this can look a bit intimidating, right? So just get used to the fact that these two mean the same thing. Okay, so the curl of this particular field is I times d by dy of this is 0, d by dz of that is minus, that's going to be minus y squared, minus j, d by dx of that is 2x z squared, minus d by dz of that, 2z x squared y squared, plus k, 0 minus d by dy of that, so that's going to be minus 2y x squared z squared. Okay. So it's very straightforward. That's the curl of that particular vector field. And again, that vector, were you to plot that vector with its I, j, and k components added together, that vector tells you the axis around which the net rotation of your vector field is at that point. Were you to have that vector field and have your microscopic light wooden ball with the pitted surface sitting in it at some point, and were you to spear it so it could only rotate in the xy plane, then the only component of the curl which would be relevant would be the component in the k direction, and the same for the other directions. Okay, so let's understand now what the magnitude of the curl means in terms of something that's easy to understand, like the rotation of a solid body. So I have some solid body, so something like this. So I have some cylinder. And this cylinder is rotating with an angular velocity omega. And this means that the angular velocity vector is omega in the k direction, and that is because we are choosing this to be our z direction in this example. And we are choosing the xy plane to lie in the plane of the end of the cylinder, okay? So I'm going to choose my x and y coordinates to be something like this. XY plane is in the end there. The Z axis is along the axis of the cylinder. And what I'm going to consider is there is some point R in this plane which has some position vector to it. Okay? So R will have coordinates xi plus yj. And that's just the position vector, that's the two-dimensional position vector of something which is in the plane, which is the end of the cylinder. Now, the velocity field created in this plane at the end of the cylinder cylinder, or in fact at any parallel plane anywhere along the cylinder, because this is rotating like a solid body. The velocity field V is the cross product of the angular rotation field with this position vector. So this is the determinant of I, J, K. Our angular rotation field only has a K component, so that's 0, 0, omega. And our position vector only has X and Y components, that's X and Y and 0. So what we see then is our velocity field has a vector field which is minus y omega I minus x plus x omega j. So you'll recall that I said about 5 or 10 minutes ago that the characteristic of a rotating field is that you have a y term in front of your I component and an x term in front of your j component, and that one of them has the opposite side to the other. So this is clearly a rotating field. However, what I mean by this is it has large scale rotation. And again, as I keep forewarning you, we're going to come across a vector field shortly which has large scale rotation but doesn't have a curl. Okay, so we have the rotation field as a function of x and y in the plane of the cylinder at the end for a given rotational angular velocity omega. Now remember, of course, the reason that we're getting these equations is because omega is an angular velocity, so it's constant, it's the same anywhere on that plane. Okay? There are many other situations in physics, of course, like Keplerian motion in a gravitational field, where things do not rotate like solid bodies, and this problem would become more complex. But this is a very nice, straightforward one, simply because it's just solid body rotation. So we take the curl of this field then. Now my x component is minus y omega. My y component is plus x omega. And my k component is 0. Now again, you can already see that because my velocity field is only operating in the xy plane, that the curl of this field is going to be in the k direction, and that's just going to tell you about the rotation in that plane. So that's exactly what we want. So if I take the curl then of this vector field, I see that I get 0, and I get 0 for the I and j components as expected. And for the k component then, I get d by dx of that, so that's omega. And I get minus d by dy of that, which is minus omega, so that's minus minus. So that's 2 omega. So the magnitude of the curl of a vector field is twice the angular velocity of a solid body which is rotating along that same axis. Okay? So this is the best handle that you can get on what the curl quantitatively means, what the value of the curl quantitatively means. I think for gradient and divergence, it's a little bit easier to think immediately in terms of the values of the vector field, what those magnitudes mean. But this is the best way of understanding what the magnitude of the curl means. It's twice the angular velocity of a solid body rotating along that axis. Okay, so again, as I say, I've forewarned you about this, but let's consider the case then of microscopic versus macroscopic rotation of a vector field. And I'm talking about rotation here. And the microscopic rotation is what we measure with the curl. And the macroscopic rotation is what we measure with for example, by intuition, our eyes, or more correctly, mathematically, a line integral. And in fact, around my vector field, and in fact, the relation between the line integral around some path in a vector field and the curl of that vector field enclosed by that line, that is in fact the basis of Stokes' theorem, which we'll be doing a week from now in the last lecture of the course. Okay, so let me consider this vector field here. So this vector field is minus yi plus xj. That's the top part of it. And let's just compare that for a moment to the vector field which we had up there for our solid body rotation. So this is just a scaled version of solid body rotation. And again, you recognize immediately now we've got a minus y in front of the I and a plus x in front of the j, so that's a rotating field. That's great, we know that field is rotating, and it's divided by x squared plus y squared. So some things to notice straight away. The magnitude of this vector is the square root of x squared plus y squared. So if I had this vector and I had written to the power of a half around that, or the square root of that, that would just be a unit vector. That would be a rotating field with unit length vectors everywhere in the field. But in fact, I've got it falling off by another power of r, so this is a vector field which gets weaker as it falls off away from the origin. So this vector field looks like this. Okay, so it's rotating around like this, but when I go larger distances from the origin, then it's falling off in magnitude. By which I mean magnitude. Okay, clearly there's a large-scale rotation in that vector field. So now let's look what the curl is like of this vector field. So in this case, the curl of our vector field is the determinant of I, j, k. Now my x component is minus y over x squared plus y squared, and my y component is plus x over x squared plus y squared, and I have no k component. So then we want to work out what is d by dx of x over x squared plus y squared. So that equals 1 over x squared plus y squared plus x over, and then I get from this, I get a minus 1, and I get a 2x all over x squared plus y squared squared. And then if I rearrange that to all be over x squared plus y squared squared, then I get x squared plus so that's what our d by dx is of that diagonal component, and we want to subtract the minus y over x squared plus y squared, so that's minus minus, so that's going to be plus the y version of that, and the y version of that is simply going to be x squared minus y squared. So we see that the curl of this vector field equals 0. So this is a well-known vector field, and it's well-known because it appears to, to counteract several rules, and in fact, in some sense, this vector field does seem to invalidate Stokes' theorem, and we will return to this vector field in lectures next week. So let's just try to think about what's happening in the case of this vector field. So if I take one infinitesimally small portion of my xy plane for this vector field, and then I blow it up very large, then my whole vector field is rotating in this sense. We know that. So there is an inner rotation or an inner torque, and there is an outer one. So we know that the magnitude of this vector field is falling off as 1 over r. But the path length over which this torque is acting is proportional to r. So this L here is proportional to r, and what we see therefore is that the drop in the magnitude of the vector with distance is exactly counteracted by the increase in the path length with distance, and therefore you get 0 rotation. And what you can see is that, in fact, if you had a vector field which fell off more rapidly with distance, you could actually have a large-scale circulation like this, but actually a sphere which was rotating in the opposite direction. So for this particular vector field, what we're actually saying is that if we had our infinitesimally small pitted wooden sphere in this flow, and in fact if I had marked on it, if I put a mark so I knew what side that was, then as that sphere went around the flow, it wouldn't rotate at all. So even when it was over here, it would still be pointing in that direction. And that is because of the form of the field is such that the torque on it, on the inner and outer edges, exactly cancels out. I think that's where we were. All right. So, what does it tell you that the curl of a vector field is 0? So, we know that if we have some scalar field u as continuous second-order partial derivatives, then the curl of that is 0. I think you understand what that means, but we're going to come to that in a moment anyway. We know that if f is a conservative field, therefore, the curl of f is 0. As a result, it's often said that if the curl is 0, that tells you that a field is conservative. That is not true. Okay? That is clearly not true from the example we just did. If the curl is non-zero, your field is non-conservative. If the curl is 0, oh, there's 3 points. I'll write them down. So point 1 is that for a conservative field, the curl equals 0. That's true. The second point is that if the curl is non-zero, this is not a conservative field. However, as we've just seen, there are non-con So it's sometimes said if you measure the curl of some vector field to be 0, that must be a conservative field. That's not true. But if you measure the curl of a vector field and you find that it is non-zero, then it's definitely not a conservative field. And again, if you look at this vector field which I've sketched up here, you can clearly see that if you started at this point and moved something round like this, then you would do a certain amount of work which would be different to the work you would have done if you had moved round like that. Okay, so that's clearly not a conservative field. Right, so we want to prove that the curl of a conservative field is 0. That's very straightforward to do, and that's very similar to, it's essentially the same as what we have done previously when we're using, when we showed the second derivative commute. So if I again return to the curl of f, then we see that the curl of f, let's consider just the I component. The I component is dfz by dy minus dfy by dz. If f is conservative, then the fz component is actually the partial derivative of du by dz, where u is some scalar potential. Right, so you know this, we've done this, and I've probably repeated it many times. If a vector field is conservative, then it's the gradient of some scalar potential, and therefore the fz term of that vector field would be du by dz, and similarly then the fy component would be du by dy. Therefore, dfz by dy is actually d2u by dz dy, and this one, dfy by dz is equal to d2u dy dz. And these two are equal because second derivatives commute. And that's an argument we've seen several times. That's essentially the same argument as the one which we've already seen previously, okay? So there's nothing particularly new or interesting about the reasoning behind the fact that the curl of conservative fields is 0. All right, so determine if the following field, as an example, determine if the following field is conservative by evaluating the curl. Now remember, if you get this kind of question, right, I've just told you, if the curl you measure of a field is 0, that doesn't prove it's conservative. So you can already see what the result is going to be of this question, right? It's obvious that the question is going to lead you to the conclusion that the curl of this vector field is non-zero, and therefore it's non-conservative. But we can work it out anyway. I times minus 2y x squared minus nothing plus k some things in here. The point is, as soon as you see the first term, you see that the curl is not 0. Right? As soon as you see the first term, you know the curl is not 0. If you work out the k term, you'll see also that that is non-zero. The curl in this case is non-zero, and therefore it's a non-conservative field. So I've been making the point that if the curl is 0, it doesn't prove it's a conservative field. You do sometimes see questions which actually make that mistake. Okay, so I would just advise you, in terms of your future exercises and career, just to bear in mind that some people actually think that the curl 0 means that a field must be conservative. Okay. Right. So I think, well, I'll get to that wrap-up slide in a moment. You will not be expected to remember what the curl is in other coordinate systems, but I've made a fairly big point earlier on in the course about the fact that if you can visualize the scale factors for your different coordinate systems, then you can use those to work out what the operators are in different coordinate systems. So this is not part of the syllabus. You would not be expected to memorize this, but I like it because it shows, we've already seen this for gradient and divergence, and it shows that if you use these scale factors, then you can always work out what these operators are in those coordinate systems. So if H1, H2, and H3 are scale factors, then the curl in any arbitrary coordinate system is given by the following. Where these are our 3 unit vectors in our 3 different axes directions in our new coordinate systems. These are our 3 coordinates, u1, u2, u3, and these are the components of our vector field in these 3 dimensions. And you can see that, as you know, for 3-dimensional Cartesian coordinate system, h1, h2, h3 are all 1. These are I, j, and k. And these are x, y, and z, and you can immediately see that this reduces to the form for 3D Cartesian coordinate system. But you can generate any curvy linear coordinate system, work out what the scale factors are, and you can work out what the curl is. And as I've shown earlier in the course, there are equivalent expressions for gradient and divergence too. All right, so let me just wrap up then on div, grad, and curl. I'm sure I've bored you senseless repeating this stuff over the last few weeks, but these are the 3 new operators which you've come across in this course: divergence, gradient, and curl. So let's just do a quick reminder of these again. The gradient takes a scalar field, often referred to as a scalar potential, and it returns a vector field whose direction is the rate of greatest change of the scalar field, and whose magnitude is the rate of change in that direction. So you have a scalar potential, which you can think of a whole load of numbers, scalar values distributed throughout your coordinate system, and if you work out the gradient at any particular point, it tells you what is the direction and magnitude of the rate of greatest change of those scalar values. The divergence takes a vector field and returns a scalar which measures the tendency of a field to spread out. Just like with the curl, what you're really doing is you're measuring the infinitesimal tendency of your vector field to diverge or converge. Okay? And again, we saw that in a way yesterday with the electric field. The electric field on a large scale clearly is flowing outwards in a sense, but on a microscopic scale is not, because the divergence is zero. So divergence takes vector, returns a scalar, and the definition of it is the surface integral as you reduce the volume to zero around some point in your vector field. And then the curl takes a vector and returns a vector, and it measures the microscopic rotation of a vector field. So the direction that your curl vector points in tells you the axis around which your hypothetical light particle would be rotating, and the rate, the magnitude of the curl, tells you about the rate at which it's rotating. Okay. And then, so next week, in the final two lectures, we're going to do the divergence theorem, and then we're going to do Stokes' theorem, which are two integral theorems which are integral to your future physics careers and make use of everything you've learned so far. Okay, thanks a lot.